Let us now look at subobjects in pre-varieties. So let's start with a pre-variety X with its structure sheaf. Remember, a pre-variety is a ringed space that is covered by affine varieties. Constructing open subvarieties is easy. So any open subset U is a pre-variety. It's a ringed space with the sheaf OU given by restriction of the structure sheaf on X. And why is it a pre-variety? Pause and think. The answer is simply that since X is already covered by finitely many affine varieties, taking intersections with U, you will get your open cover of U. And these intersections, being open subsets of affine varieties, are in turn covered by principal open subsets, which are affine varieties. This works because subsets that are open in U are open in X. So to speak, go back and forth, and you can define the structure sheaf as taking subsets of U. Knowing that these subsets are open in X, you can plug them into the structure sheaf on X. Why am I saying this lengthy thing? It's because the same thing would not work if your subvariety U is replaced by a closed subvariety X. Then you cannot just say, okay, take an open subset of Z and plug it into the structure sheaf on X, because this will not be an open set, so this will not be well defined. Therefore, we do the following thing. We say that a closed subset of X is a pre-variety with the structure sheaf defined by the set of all functions that are locally regular at each point of an open set U. So what does this mean? We use this terminology in this slide, that a function phi from U to K is locally regular at A in U if there is an open V in X containing A and a regular function in X on this V that coincides with phi on the intersection. So the picture is the following. If this is my Z and X is the plane, then this set U, I look at an element A in U, then I will find a set V open in X so that my function coincides with the restriction of some regular function on V to the intersection. And one can check that this makes the inclusion of Z to X into a morphism of pre-varieties, a morphism of ringed spaces. Now, let us look further into subsets. So if we have a morphism of pre-varieties, F between a pre-variety X and a pre-variety Y, then if U is an open sub-prevariety of Y, then its inverse image is an open sub-prevariety of X. This is because inverse images of open sets are open because the function is a morphism of prevarieties, and so in particular a continuous function between these topological spaces, so everything checks out as usual. And the same holds for closed sub-prevarieties because the pre-image of a closed subset is closed. However, direct images are in general neither closed nor open. So if W is an open or closed sub-prevariety of X, then F of W doesn't have to be one. And so I give it to you as an exercise to construct examples where this bad thing happens. The general warning that is related to this failure of direct images to being sub-prevariety is that we don't have a general notion of sub-prevariety without closed or open. You cannot take an arbitrary subset and declare it in a natural way a sub-prevariety. You can do this with open subsets, closed subsets, but already when you take unions of one open and one closed subset, you run into problems. One construction that is important and that will be important when we want to exclude these bad prevarieties is that of the product. So let us go back a bit and look at products of affine varieties. And indeed, let us go all the way back to algebraic sets. So if we have an algebraic set X in affine M space and an algebraic set Y in affine N space, then their product, simply the set of all x, y, such that x is in x and y is in y, their Cartesian product, is an algebraic set in A m plus n. So this means that if we have two affine varieties, then we can define this construction and call it their product. And when we do this, we do not look at the product topology, we look at the Zariski topology. So as an example of why these two are different, let us look at A1 times A1, which is A2. So any curve in A2 is an affine variety, so it is closed in the Zariski topology in A2, but it is not constructible as a product of closed subsets from each of the A1s. One thing that is important to mention is that since we're talking about these as affine varieties, what is the structure sheaf of X times Y? And so since this is an algebraic set and affine varieties, we have seen that the structure sheaf of an affine variety is completely determined by the structure sheaf of the variety itself. So the coordinate algebra of this thing. And it turns out, this is an exercise for you to show that this is the tensor product of the two coordinate algebras. And this defines the structure sheaf of the affine varieties. It is not so important now for us that this is the tensor product, but just to note that indeed x times y, defined in this fashion, is an affine variety with a proper structure sheaf. But we cannot just define a product randomly. The notion of a product in a category is a well-defined thing, and it's defined in terms of a universal property. So we need to check that this product is actually what we want to call a product, and namely that this product satisfies the universal property of products. First, note that the projection maps from x times y to x and to y are morphisms of affine varieties. Now we can state the proposition that x times y satisfies the universal property of products, which is the following. In words, for any affine variety z and morphisms from z to x and z to y, there is a unique morphism from z to x times y composing with these morphisms. In pictures, this means that if I have x here and y here, then my product should be such that for any affine variety z and maps fx and fy, there should be a unique map here, f, such that when I compose it with the projections pi x and pi y, I get my original maps fx and fy. So this is the universal property of a product. And so why is this true for our definition of the product? Well, the conditions that fx is pi x f and fy is pi y f force f to map z to fx of z, fy of z. So uniqueness is guaranteed because this is the only way that this can work. And why is this a morphism? So why does this thing exist? Well, we have agreed and seen in a proposition that a map between ringed spaces is a morphism, between affine varieties is a morphism if the coordinate maps are regular. And so because we know that fx and fy are morphisms, so their coordinate maps are regular, patching everything together, we will get a morphism. So indeed, the product, as we defined it by hand, so to speak, of affine varieties is the right notion of a product of affine varieties. Now we want to generalize this to a product of pre-varieties. And we will define it in the following way, that given x and y, if they are pre-varieties, then the claim is that there is a pre-variety that we call suggestively x times y, with morphisms pi x from x times y to x and pi y from x times y to y, satisfying the universal property of products. So this property that we had on the previous slide, that for any z and maps fx and fy, now z a pre-variety and fx and fy morphisms of pre-varieties, there should exist a unique f making this diagram commute. So we have products in the category of pre-varieties. So how do we show that there exists such a pre-variety? Well, we construct one. So also we will show that it is unique up to a unique isomorphism. The construction is as follows. As a set, it will be just the Cartesian product of sets. And since we have an open cover of x and an open cover of y, we will get an open cover of x times y, where this product here is the product of affine varieties that we defined on the previous slide. And we are assuming that the ui's and the vi's are affine open sets covering x and y respectively. Constructing this set is done as follows. So how do we construct this pre-variety? We construct it by gluing, as in the previous video. So what we do, we take the products of these ui's and vj's and glue them along the identity maps of their intersections. And so this will give us a pre-variety that we will call x times y. And then we need to provide these pi x and pi y. And we do those by gluing together the projections of products of affine varieties from ui times vj to ui. So this is the restriction of pi x. And from ui times vj to vj, this is the restriction of pi y, what will be. And then we glue them together to get pi x and pi y. And we check that the universal property is satisfied for these. I leave it as an exercise. It's tedious, but not very instructive. So now let us go back to our original question. How do we exclude the line with double origin from being a desirable variety or pre-variety? So in topology, how do you do this? In topology, when you study manifolds, you require manifolds to be Hausdorff. Hausdorff means that given any 2 points, you should be able to find an open set U containing 1 point and an open set containing the other point, and these open sets should not intersect. This excludes the line with 2 origins because any such U and V will have to contain some other points, and then they cannot intersect in an empty set. They have to have a non-empty intersection. In algebraic geometry, unfortunately, we do not have access to the Hausdorff property. If we required spaces to be Hausdorff, things like already the affine line would be excluded, and we do not want to do that. So looking back into topology, we see that the Hausdorff property can be proved to be equivalent to the following property. The diagonal is closed in the product with the product topology. So this is an interesting result that says that a topological space is Hausdorff if and only if the diagonal, so the set of pairs x comma x with x and x, is closed in the product space, but under the product topology. We are not using the product topology, remember, we're using the Zariski topology on the product, but still let us see if we can use this property. So we call a pre-variety separated if it satisfies this property, namely that the diagonal is closed subset of x times x, but x times x with the topology coming from the product construction that we just saw. And a separated pre-variety is called a variety. So this is the moment where we drop the prefix pre and talk about an algebraic variety. An algebraic variety is a separated pre-variety. And we use the words curves, surfaces, and hypersurfaces to talk about algebraic varieties of dimensions 1, 2, and n-1 in some variety of dimension n, as we did with affine varieties. So let's look at some examples of algebraic varieties. Any affine variety is a variety. I leave it to you as an exercise to realize the diagonal as the zero set of some polynomials. Any open or closed sub-prevariety of a variety is a variety. This is because if you have a variety X and such a sub-prevariety Y, then you consider the morphism from Y times Y to X times X. That is simply inclusion. This exists by the universal property on the product. And then you check that the diagonal in Y is just the pre-image of the diagonal in X. And so it is closed because delta X is closed because X is a variety. So you drop the prefix pre and talk about open and closed sub-varieties. The line with 2 origins is not a variety. So this line here with 0, 1, 0, 2, in x times x, the diagonal, so if this is x, the diagonal delta x will contain 0, 1, 0, 1 and 0, 2, 0, 2, but not 0, 1, 0, 2 and not 0, 2, 0, 1. So it will not be closed. With varieties, we can perform some constructions. So if we have a pre-variety x and a variety y and a morphism between them, we can look at the graph of this morphism. This is the set of all pairs x, y, where y is f of x. The claim is that this is closed in x times y. Why is that? This is because gamma f is the pre-image of delta y under the map f, identity from x times y to y times y. And so therefore, since y is a variety and delta y is closed and f is continuous, this will be closed. And in the same way, you can show that if you have x a pre-variety, y a variety, and f and g two maps, then the set of all x, where f of x and g of x are the same, is closed in x. I leave it to you as an exercise to construct a map whose pre-image is this of the diagonal and show that this therefore has to be closed.